Welcome everybody to another video lesson. We are continuing our 8.2 concepts. We're looking at unit vectors today, and our objective for this lesson is to be able to write vectors as linear combinations of unit vectors. So let's hop right into what a unit vector actually is. It is just a vector, any vector, with a magnitude of 1. Okay, magnitude is just 1. So if I have unit vector u and any vector, non-zero vector v, we can find the unit vector for v by taking v and dividing it by our magnitude. Okay, dividing v by the magnitude. Now I know we didn't learn how to divide vectors, so we can think about this as multiplying instead by 1 over the magnitude of the vector. Right? Now, 1 over the magnitude is just going to be some number, right? That's just a scalar value. So we've actually seen this before. We know how to do this, multiplying a vector by a scalar, okay? So that's how we can find the unit vector of any vector, okay? It's going to be going in the same direction. It is just 1 unit, okay, instead of having a magnitude of, more than 1, okay, or less than 1 or whatever. All right, so let's take a look at unit vectors in our xy plane. Okay, so I've got my xy plane here. Let's see, we'll make this x, we'll make this y. All right, now our unit vectors, there are 2 that are going to be very important for us, and those are unit vectors I and j. Okay, unit vector I is the unit vector in the direction of our positive x-axis, so going this way. And then unit vector j is going in the direction of our positive y-axis. Okay, so it's going up 1. Now we can represent any vector in terms of these unit vectors, and that's what our linear combinations are. That was our objective for today's lesson. So if I have vector v, right, and we can represent this in component form like so. Now, hopefully you can see if I were to multiply my unit vector I by 3, right? That's just the horizontal component for this vector v, right? Okay, we've got 1, 2, 3 unit vectors going in our positive x direction, and then same for our positive y direction. If I have 2 j unit vectors, then we make up the vertical component of vector v, right? So I can think of v in terms of unit vectors, okay? So we can see here that what are the components, or what's the component form of I and j? Well, for I go over 1 in the x direction, and then I don't go up in the y direction at all. So that's going to be 1, 0. It's going to be our component form. And similarly for j, I don't go anywhere in the x direction, but I do go up 1 in the y direction. So our component form is 0, 1 for unit vector j. Now I'm going to take a look at v in terms of the combination of 2 vectors, right? So our horizontal and vertical components for unit vector v, we can write like this. And let's see, what our vertical component looks like is just, like I said, 2 j unit vectors. So the component form would be 0, 2 for the vertical component of v. And the horizontal component is going to go over 3 and up 0. So 3, 0 is our component here for the horizontal component for v. All right. So if we wrote that as the sum of 2 vectors, and again, we can think of this sum geometrically. If I were to go tip to tail here, if I moved my vertical component over and moved my horizontal component up to the origin here, then we would land right here at 3, 2, and our resultant vector would be v, right? So we can represent v as the sum of these 2 vectors, 3, 0 plus 0, 2, right? Now, I can think of this a little bit differently in terms of our scalar multiples, right? Hopefully you can see that if I were to kind of factor out, not really factor out, but I'm going to represent this 3, 0 in terms of 3 times the vector 0, or 1, 0, okay? 3 times 1, 0. So if we were to go ahead and multiply this 3 through, we would get 3, 0, which is what we have up here. Okay, so these 2 terms here are the same, right? And same here for our 0, 2. I can kind of bring out this 2, and I'm going to represent this as a scalar multiple here, and these guys are the same as well. So if I multiply this 2 through, I get 0, 2, which is what we have here. Okay, so I'm just representing this in a little bit of a different way to show you that we have 3 times this 1, 0. Well, 1, 0 is the component form for our unit vector I, right? Plus 2 times 0, 1, which is the unit vector j component form. So I'm going to go ahead and substitute in I and j where I see 1, 0 and 0, 1. And I can actually represent v in terms of I and j as 3i plus 2j. Okay? So this is for this particular unit, or this particular vector v, but any vector, okay, so we'll have a generic vector ab, we can represent as a times the unit vector I plus b times the unit vector j. Okay, and this is what we talked about when I mentioned linear combinations. So if you're asked to represent a vector as a linear combination of I and j, this is the format that you are going to be converting to. Okay, so let's go ahead and get into some examples then. Okay, if we are finding a unit vector with the same direction as our given vector here, okay, let's go ahead. We're going to convert vector w with the component form 6, negative 2, and we're going to find our unit vector here. And remember, our unit vector, to find that, we're going to have the vector divided by the magnitude of that vector. So here I have my vector, but I need to find the magnitude, all right? Which we know how to do that. That's going to be the square root of our first component plus this, or the first component squared plus the second component squared here, which we did in the previous video. So that's going to be the square root of 40 there. So I can think of my unit vector as 1 over the square root of 40 times my vector. So again, this is just a scalar value, right? Times my vector. Now I'm going to go ahead and rationalize this 1 over root 40. So that's going to simplify to 10 over root 20. So now I can say, okay, root 10 divided by 20 times our vector w. That's going to equal root 10 over 20 times 6, and root 10 over 20 times negative 2, and that's going to simplify here to this would be our unit vector for vector w. All right, so that is the process of finding our unit vector. Go ahead and see if you can pause the video and find the unit vector for x. All right, here is the process. To first find the magnitude, then you just go ahead and multiply by 1 over that magnitude. Don't forget to rationalize your denominators, like so, and you can find your unit vector. Now, I want you guys to see something here. You can easily check your work here, and if you're asked to check your work, this would be how you would do it. If you find a unit vector here for x, well, what does the magnitude of u have to be? Well, it has to equal 1, right? So you can go ahead and find the magnitude of your unit vector, and if that is 1, then you have found the correct unit vector for your whatever vector that you were starting out with. All right, so a quick way to check your work, again, is just finding the magnitude of that unit vector. All right, let's take a look at some linear combinations now. Okay, we're going to write AB as a linear combination of vectors I and j. All right. So first thing we want to do is we want to put AB into component form. Okay, we want to put that in component form, which we know is going to be x2 minus x1 and y2 minus y1. So let's see, I've got x1, y1, x2, y2, because A is going to be my starting point, my initial point, and B will be my terminal point. All right. So then we can go ahead and plug those values in, and we get component form of 8, 5, which we can represent as 8 unit vectors I plus 5 unit vectors j. All right. So go ahead and pause the video and see if you can do that again here on the right-hand side for AB. Okay, here is the process that we can find AB in terms of a linear combination, negative 4i plus 9j. Now, something to be aware of, guys, do not get this confused with imaginary numbers, okay? Unit vector I does not equal imaginary. It does not equal an imaginary number. Okay, and same with j. Sometimes you saw j representing imaginary numbers. Okay, so don't get confused here and think, oh, are we working with imaginaries? What's going on? No, we're working with unit vectors, and that is very different from imaginary numbers, so don't get confused there when you see unit vector I and unit vector j. All right, a couple more examples. We're going to find the component form of our vector with a given magnitude and direction. So we're given v. Now let's think about this here. We got our magnitude and our angle. We want to find our component form. So if this is v, okay, at 45 degrees roughly, right? That's our theta, whatever theta is, more of a generic concept here. Okay, we know that we have a horizontal component here and a vertical component here. Now, if v had a magnitude of 1, okay, then the horizontal component here would just be cosine of theta, right? And the vertical component would be just sine of theta, right? But if v has any other magnitude, right, then it's not just going to be cosine and sine, right? It's going to be that magnitude times sine. And for the horizontal component, it's going to be the magnitude of our vector times the cosine, okay? Which hopefully you can remember that from some trig identities that we've worked with in the past. So we're going to go ahead and apply that same concept for vector v here. So we've got a magnitude of 8 at 45 degrees, and we just need to find our x and y components because we're putting this in component form. Okay, so x is going to be our magnitude times the cosine of our theta, which in this case is 45. So that's going to be 8 times root 2 over 2, which will simplify to 4 root 2. Same thing for our y component. We'll have the magnitude times the sine of 45. That's again going to be 4 root 2. So we can write our component form like so. We can either leave it as a radical, or this is when we are converting to decimals, whichever one you're asked to do. Okay. So go ahead and pause the video one more time and see if you can't find the component form for this right-hand example. Okay, here is our final component form. Okay, keep in mind that our theta is going to be our standard angle, right, which is the angle that is created going counterclockwise with the positive x-axis. Okay, so this is my angle theta. We're not going clockwise, we are going counterclockwise always with these angles. All right, let's take a look at another example here, finding direction angles. We're going to find the direction angle of our vectors, okay? So remember, we go back to our diagram here, okay? We know that we can express our horizontal and our vertical components in terms of the magnitude and the angle theta here that we're making with the x-axis. What if we're asked to find theta? That's kind of what's going on here. Well, we can do that by using our trig identities here. Okay, so theta is going to be sine over cosine, or in this case, it's going to be the magnitude times the sine over the magnitude times the cosine, and this should have little magnitude marks there. There we go. Okay, so that is what we're doing here when we find our direction angles. Okay, now if we are expressed in a linear combination like we have here, okay, we've got a times vector or unit vector I plus a b times unit vector j, right? So what does this kind of simplify to? Well, this is one component, right? This is the horizontal component. This is the vertical component that's equal to the magnitude cosine and the magnitude sine, right? So we can actually simplify this to just be b over a. So tangent of theta is equal to b over a. So let's go ahead and use that understanding to go ahead and find our direction angle for these vectors here. So I've got negative 6i plus 2j. So let's see, the tangent of theta, again, is going to be b over a. So that's going to equal negative 2 over 6. Okay, so if I take the inverse tangent of both sides here, then we'll have inverse tangent of negative 2 over 6. That's going to give me this angle of negative 18.43 degrees. Okay, but think about what we have going on here. Okay, I've got negative 6, okay, moving in the x direction, and then positive 2 going in the y direction. So that's going to look something like this, right? Okay, so that negative 18.43, what do we think that actually is? Because clearly that's not this angle right here, our standard angle. What that actually is giving us is, because our standard angle is with our x-axis and it's going counterclockwise, this is going with our x-axis, but it's going to go it's going to go clockwise this way. Okay, so what we just found was this angle right here, which is not what we're looking for when we look at a direction angle for a vector, right? We are looking for this angle theta here, our standard angle with our positive x-axis. So we need to kind of think about what theta actually is, right? Okay, because again, we want this standard angle going counterclockwise from x, okay, or from the positive x. So knowing that this is going to yield 180 degrees total, if I add this theta with this little red angle that we just found, okay, then I can go ahead and just subtract 18.43 from 180, and I find that theta is equal to 161.6 degrees, right? So with that same thought process, go ahead and try this one. Keep in mind that -3, -8 is going to put me in what quadrant? It's going to be quadrant 3, right? So pause the video, see if you can find your angle theta. Okay, here's our process. Again, we're going to be in quadrant 3, and when you first do the tangent of 8/3, it's going to give you 69.44. Okay, that is obviously not what this standard angle is from the positive x-axis. That's just going to be this angle from the negative x-axis here. And so we need to think of this in a little bit more context and add 180 to that, and we get an angle of 249.4 degrees. Okay, one more example here. We're going to look at some applications. Okay, a soccer player is running forward. We've been doing a lot of soccer, kicking the soccer ball around. But a soccer player is running forward at 7 meters per second and kicks a ball with a velocity of 30 meters per second at an angle of 10 degrees with the horizontal. What is the resultant speed and direction of the kick? Of the kick is what we are looking for, okay? So you guys know how good I am at drawing. I had to make a little sketch of this one. So we've got our soccer player. Now we've got vector S, okay, for speed. They're running at this at a magnitude of 7 meters per second, and then they kick with the magnitude. So we've got vector K with a magnitude of 30 meters per second at an angle of 10 degrees, right? So let's go ahead and place our vectors on our XY axis here. And we're going to go ahead and go tip to tail with this, okay? Tip to tail. So we start off with 7, and this is of course not drawn to scale, but we start off with 7, and then we go at an angle of 10 degrees with our tip to tail with our angle, or with our vector of 30, right? So now what we're really finding is our resultant of these two vectors here, okay? So that's going to be this vector R right here, right? Okay, we just go from our initial point to our terminal point. That's going to be vector R, okay? So what we've done here is we've just added vector S and vector K, right? We've added those two together to find R, right? Vector S, we know we can express in component form as 7, 0, okay? Because it has a magnitude of 7 and it's going completely horizontal, so no vertical component there. Vector K, however, okay, so we know that the magnitude times the cosine, that's going to be the horizontal component of vector K, and then the magnitude of K times sine of theta, that's going to be the vertical component for K. So that's going to be 30 cosine 10 and 30 sine 10. Okay, so R, vector R, is going to have components of 7 plus 30 cosine 10 and 0 plus sine of 10, all right? So in decimal form, we've got 36.54 and 5.21. So that would be our resultant vector right there. But it is asking for the speed and direction of the kick. Okay, so the speed, the resultant speed, that's going to be the magnitude of our vector here, of our resultant vector, right? So we need to go ahead and find the magnitude, which we know how to do. That's just going to be the square root of our components squared and then added together. So if you plug this into a calculator, you'll get an approximate magnitude of 36.9 meters per second. Now we need to find the resultant direction of the kick. So we need to find this angle right here. We need to find that angle right there. Okay, so we've got tangent of tangent theta is going to be b over a, which in this case is 5.21 over 36.54. Take the inverse tangent of both sides, and we get an angle of 8.1 degrees. All right? So that is it for this lesson, guys. Good luck with your practice.